Morning, everyone. We're a bit early today, so if you have questions, we can answer those. Are there questions while we're waiting? Anybody? Go ahead. 263, it's all good. Well, I hope I'll be able to answer, but I don't really understand where epsilon delta come from. It's easier to explain it in the one-dimensional case. Remember, we say a limit as x goes to a of f of x is L. If f of x can be made arbitrarily close to L by taking x sufficiently close to a. Or, epsilon greater than 0 given, there exists a delta greater than 0 such that if x minus a is less than delta, then f of x minus L is less than epsilon. So f can be made arbitrarily close to L by taking x sufficiently close to a. On a graph, we're saying that if you restrict your attention to values close to a, how close? Delta close. Right? So if you take any value of x in here, where this is a plus delta, a minus delta, right? So for any x in here, you are mapped to somewhere in this box, L minus epsilon, L plus epsilon. So every value in here gets mapped somewhere in here. That's the one-dimensional case. And then it extends. take any point AB, you get a disk of radius delta, and that has to map to somewhere in this box, and so on and so on. If you want to prove that the limit exists, epsilon delta, you have no choice. The 263 question was, what does the Vronsky show? Wait. How do we know a solution to a second order ODE is a unique one? When you say that, you mean second order with initial conditions, right? Second order with initial conditions, because if it's just a second order differential equation, you really expect, right? So yes. So how do you prove that it's unique? And so if you have a second order, first of all, let's assume it's linear. So you have a linear operator on Y, and this is going to be equal to some function of X. And if you have two solutions, then of course the linear operator on the difference is going to, well, I mean, this is L of Y1 plus L of Y minus L of Y2. And this was f of x, and that was f of x. So everything is 0, right? The beautiful thing here is that it all comes back to linear algebra. A differential equation is really a linear operator. So that's very interesting. Shell is suggesting instead of epsilon delta, you could use r theta, drawing a disk, and that's nice too, right? I mean, that's possible as well, but you're going to want to show that the image is still in this box. Absolutely. And that's the thing, right? I mean, when you're taking, as Noloy points out, you have to learn to love linear algebra. What happens is that, you know, you're taking 133, you don't like it all that much, you don't see the point, but later on, you recognize that a lot of things can be done using linear algebra. Everything comes back to linear algebra. So what's my point here? If you have two solutions, then the difference is a solution to the homogeneous equation. So instead of proving uniqueness for some function, really, you can assume that it's homogeneous. So how do you prove? Well, using the Vronskian, you can show that if you have two linearly independent solutions, then any other solution has to be a linear combination of those two. That's not... Is that clear? That's not really using the Bronskin though. Here. What was your question again? Were you just looking for... Let me scroll back up to your question. How do you know the solution is unique? Yeah. So you have to prove. So you're not asking for the existence of a solution, you're just asking for uniqueness. So that's like asking for uniqueness of the equation, of the homogeneous equation with these particular with these initial conditions. There it is, there it is, there it is. We'll bring it back to calculus. All right, so for those of you just joining us here, here's the question. If you have, let's call it a second order linear differential equation, why is the solution unique? Second order differential equation with initial conditions. Right? And this idea brings it back to so without loss of generality, you can assume, so without loss of generality, you can assume a homogeneous second order differential equation with initial conditions y of a is equal to 0 and y prime of a is equal to 0. Right? And now you've got your second order differential equation. So you're going to have a y double primed in there. Right? Your L of y is equal to 0 involves a y double primed. So even if it's not linear, you're still fine. It involves a y double prime, so solve for y double prime. You get y double prime equals some function of x, y, and maybe y prime. But when you plug in A, since y and y prime are 0, This is also going to be 0. So I guess you had to go with the linear to begin with. This is also going to be 0. Right? I mean, what am I talking about? Y double prime plus P of x y prime plus Q of x y. Right? So I'm saying solve for y double prime. So you get minus P y prime minus Q y. And when you plug in A, what happens? Minus P of x A, y prime of A, minus Q of A, y of A. But this is 0. Or right here. And this is 0. So the second derivative is 0. All right. Well, differentiate. Differentiate. We have y double prime as minus P y prime minus Q y. If you differentiate, y triple prime. So, you're going to get the derivative of this. Minus P prime y prime minus P y double prime minus Q prime y minus Q y prime. And plug in A again. Well, this is 0. This is 0. You just work that out. This is 0, and that's 0. So the third derivative is 0. And so on and so on. All the derivatives at A are going to be 0. What does that mean? By the Taylor series, y, which is the nth derivative at A over n factorial, x minus a to the n, all of these things are 0. So y is equal to 0, unique solution. You can. I think, though, a Taylor series argument will work here. Right? If you do a Taylor series argument, I think you're fine. All right, anyways. All right, moving on back to what we were doing last time, namely limits. And, we're extending the idea of limits from the one-dimensional case. We are. We're doing 262. We're starting right now. We were just waiting. We were just talking until everybody comes in. Welcome, everyone. So we were looking at limits. We were looking at limits last time, and everything you know about limits extends to higher dimensions as well. What am I referring to? A limit of a sum is the sum of the limits. Limit of a product is the product of the limits. This is, of course, assuming the limits exist themselves, right? Limit of a quotient is the quotient of the limits as long as the limit of the denominator is not 0, and so on and so on. So everything extends from the one-dimensional case. Does L'Hopital's rule also extend to higher dimensions? It doesn't immediately. Maybe there's a way to extend it. I haven't given that any thought. I've never seen it done. We have lectures from now on. I don't think there are any more days off. So, I mean, even if the exam is released, we still have class. Right, so after limits, what do we do? Well, I mean, continuity, definition. A function f of xy is said to be continuous at the point AB if the limit as xy goes to AB it exists and is f of AB. So exactly the same definition as in the one-dimensional case. Of course, you understand that since limits have an epsilon delta definition, then of course continuity, which is itself a limit, has that same epsilon delta, has an epsilon delta equivalent reformulation. I won't write it down, but you know what it is. I'm stating these definitions in 2D, right, in the xy plane, but of course these extend to higher dimensions. So same with the limit, same with continuity. All of these ideas extend to higher dimensions. And, you know, the same result as we encountered in the one-dimensional case extends here as well. What do I mean by that? If you take two continuous functions and you add them together, you still get a continuous function. If you take two continuous functions and multiply them together, you still get a continuous function. Quotients, compositions, and so on, everything is continuous. Let's take an example. All right, consider this. Let's discuss the continuity of f. Well, you know x squared is a continuous function in one dimension. So you can prove it using the epsilon delta definition, and the proof is going to be the same in 2D. There's no y there. Similarly, this one as well. Right? In fact, you can say that any polynomial in x and y is going to be continuous. And since the limit of a product is the product of the limits, and limit of a sum is the sum of the limits, any polynomial, any powers of x and y and sums of these are going to be continuous. So here you've got a polynomial in x and y, so this is continuous. Same with the numerator here. The numerator is going to be positive as well, and the quotient of continuous functions is continuous as long as the denominator is not zero. So everywhere except possibly at zero, the function is going to be continuous. So everywhere except possibly at the origin, the function is continuous. Is it continuous at the origin? Well, let's check. We have to evaluate the limit. We have to evaluate the limit as xy goes to 0, 0. So you know what to do. Let's test a few. What is the, Eloy's asking, what is the 2D equivalent of 0 plus and 0 minus? As you know, there isn't, right? Because if you're going to 0 from the left or from the right in the one-dimensional case, there are only two ways to go. But if you're allowing in 2D, now there's infinitely many ways to go to 0. So not just from the left or from the right. And that's why the epsilon delta definition is crucial here. There's no other way to go. Louis, on an exam, you could just say that a rational function is continuous everywhere it's defined. Absolutely. Noloy, I think you're referring to polar coordinates. Let's not go there. Somebody had suggested that beforehand as well. Let's evaluate this limit, right? So first of all, we're going towards the origin. So let's test on the x-axis if y is 0. So if y is 0, what happens if y is 0? The numerator is 0. The denominator is x squared, so that limit is 0. So if the limit exists, it has to be 0. And if we look at if x is 0 on the y-axis, limit as y goes to 0. When x is 0, the numerator is 0, the denominator is y squared, that limit is 0 as well. All right, looking good. We can test somewhere else, maybe a straight line, y equals mx, right? Maybe all the straight lines. So if y is mx, we're looking at the limit as x goes to 0 of 3x squared mx over x squared plus m squared x squared. And if you factor out an x squared from the denominator, these x squares cancel out. Numerator is 3mx, which still goes to 0. Denominator is 1 plus m squared, which is not 0. The whole thing is 0. So on every single line, the limit is 0. You can test for parabolas if you want. I'm going to stop doing that now, but I'm starting to think that the limit actually is 0. So now let's prove it. Exactly that. So here's our claim. The limit as xy goes to 0, 0 of 3x squared y over x squared plus y squared is 0. And again, let's take a moment to write down what needs to be proven. We must show that for epsilon greater than 0 given, there exists delta greater than 0 such that if then your function minus the limit is less than epsilon. So start with that. 3x squared y over x squared plus y squared. Very good. Which is 3x squared absolute value of y over x squared plus y squared, right? The only thing that's not positive is perhaps the y. All the other terms are all positive. And now, if you make the denominator smaller, you make the whole thing bigger. So I'm going to make the denominator smaller by getting rid of the y squared. And these cancel out. This is, of course, assuming x is not 0, right? Why are we getting rid of the y squared specifically? You'll see. The short answer is that it works. And you're left with a 3 absolute value of y. But this you recognize as 3 square root of y squared. And now I'm going to add an extra term, namely an x squared. I'm adding something positive, so I'm making the whole thing bigger. Right? Malloy is asking the real questions here. What's the intuition? Well, you have this. This is what allows you to make everything small. Right? It's this delta which allows you to make everything small. You want to make this thing very small. You don't have any control over epsilon, but you do have control over the delta. And what is this? In this case, this thing, the modulus of xy minus 0, 0, I mean, we've seen this before. You know that it's the square root of x squared plus y squared. So if you can get this, you know that this can be made as small as you want. And once you know it, we now have it. We have it right here. By doing this little manipulation, we end up with what we wanted. So if you can make this less than epsilon, you're good. And you can do that by taking delta to be epsilon over 3. In that case, this is going to be less than 3 delta, but delta is epsilon over 3. And there you have it. This, which is this, is less than epsilon. We're done. Assuming x was not 0. But of course, if x is 0, this thing is just 0, which is itself less than epsilon. So in either case, we're done. We've done enough. Somebody's asking for an example where the limit does not exist. Well, when the limit doesn't exist, you don't resort to epsilon delta. You just show 2 paths where the function behaves differently. Y delta is epsilon over 3 because it works. Because it works. Our goal is to make this less than epsilon. And this can be made less than delta. So you have a 3 delta here. So if delta is epsilon over 3, it works. Gabriel is asking what happens if you try to prove continuity and it doesn't work, or if your intuition was wrong. Well, then you're never going to be able to make it less than epsilon. So the proof is not going to work. And when it's not working, you have to ask yourself, perhaps I was wrong. And then you go back to your function and see what happens. And Mathieu is asking if you cannot find 2 paths that disagree, and you try to use the epsilon technique, what would happen? It wouldn't work. You could not make your thing less than epsilon. That's all. So the goal is to make this is our goal. Right? I mean, that's why I keep writing it every single time, so that we don't lose track of our goal. You can set delta to be whatever you want. That's the thing. You have no control over epsilon, but you have complete control over delta, as long as it is bigger than 0. All right, let's move on. We've wasted more than enough time on this. I understand it's difficult. I know it's very demanding, but there's no way around it. Deloy is exactly right there. y is the expression between something, between absolute values equal to the square root. I'm not sure, Marie, what you're asking. All right, let's move on. Move on to think back to calculus 1, limits, continuity. What did we do then? We went to the derivative, right? We were using the definition of a limit to define the derivative. We're going to do exactly the same thing here. Definition. Let f of xy be a function of two variables. We define the partial derivative of f with respect to x denoted df dx, and these are squiggly d's, right, as opposed to the straight d that we had in the one variable case, right? So df dx or d by dx of f of x y or fx of xy or f1 of xy. These all mean the same. They all mean the partial derivative of f with respect to x. One here as in the first variable. All of these, also sometimes dx, I do not have that, dx, fy, or even d1. So many notations for the same thing. As the limit, as h goes to 0, of f of x plus hy minus f of xy over h. Similarly, right, yeah, sorry, you know, I realized that we didn't really finish the question before, the question before. We found the limit to be 0, right? That's not enough for continuity, though. The limit should also be f of 0, 0 in this case. But that was really how f of 0, 0 was defined. So our function was continuous everywhere except possibly at 0. We showed that it was continuous at 0, and consequently it's continuous everywhere. Our end goal is not to make delta less than epsilon. Our main goal is to make f of xy minus L in absolute value less than epsilon. But let's move away from that into partial differentiation. I have defined the partial derivative of f with respect to x as this. Similarly, the partial derivative of f with respect to y, df dy or d by dy of f, or fy, or f2, or dy, or d2, right? 2 being the second variable. This is the limit as k goes to 0, f of x, y plus k minus f of x, y all over k. Oh, is it, geez, it's a new record. All right, sorry, I didn't realize we were buffering. But partial derivative of f with respect to y is the same thing. Right. I mean, of course you understand that there's no real reason to use another variable here. I'm using k. That's the usual notation in use. But if you want to call it h, it's the same thing. Geometrically, what's happening? It's a valid question. You have this function hovering above, right? Z equals f of x, y. And if you fix a point x, y, look at its image, what we're doing is we're slicing this graph in the x direction. So if you were to slice that, right, parallel to the x-axis, right, you see what's happening. You have this function hovering in 3D and slice it, cut it, parallel to the x-axis. What's going to happen? You're going to have an edge. You're going to have a curve on the edge. And now it's the regular 1D thing. We ask the question, what is the slope of the tangent line here? Similarly, if you cut it parallel to the y-axis, you get a curve. And you ask the question, what is the slope of the tangent line here? So slope of the tangent line on the curve that you cut along the y direction or along the x. Let's take an example. Exactly that. If you cut parallel to the x-axis, you're taking the partial derivative with respect to x. Well, not the xz plane directly, but a plane parallel to the xz plane, right? Because the xz plane is right here, whereas we are somewhere here. So a plane parallel to that. Let's take an example. How do you know which x you are cutting? Well, whatever x you're given, or x, y in general, right? If they were asking for, think back to Cal 1. When you're taking the derivative at x equals 3, you know how to do that. But then when you're taking the derivative for any x, you know how to do that as well. That's exactly what we get here. Here we're going to get a rule for the partial derivative at any xy. Right, in the same way that the derivative of a function of x gives you a rule for the slope of the tangent line at any point x. Let's consider the partial derivative of f with respect to x. By definition, this is f of x plus h y minus f of xy all over h. Let's evaluate that, see what happens. So everywhere you see an x, you replace with x plus h, the y's remain. So that is x plus h minus f of xy minus the original all over h. Expand all of this. Or let's not expand and let's be smart. Let's be smart, and we're going to group these two things together. And we're going to group these two things together. And then the minus 2y squared plus 2y squared, these cancel out nicely. So I'm not expanding because I want to point out what's going to happen. And I think this will illustrate it quite nicely. Let's split that up into two pieces. X plus h squared minus x squared over h. And here, if I factor out a y, I have an x plus h minus x over h. And observe what happens. This part, if you take a step back, you're going to recognize this as the derivative of x squared, right? From Cal 1, it's really just the derivative of x squared. And you know what the derivative of x squared is. It's 2x. Here, y doesn't depend on h. So that's just a constant. And here, with the limit, you recognize this as the limit definition of the derivative of x. Exactly that. Thank you. Whose derivative is 1. So what's happening? The x's are being differentiated and the y's are being treated as constant, right? If you differentiate x squared, you get 2x. Here, y is treated as a constant. Derivative of x is 1. Y is being treated as a constant. The derivative of this is 0. Let's repeat with the derivative with respect to y. I think you have a feeling of what's going to happen. right? This is xy plus k minus f of xy over k. That's just the limit definition of the partial derivative. So here, everywhere you see a y, you replace with y plus k, and the x's remain. So that is x squared plus x y plus k minus 2y plus k all squared. Here the x squares cancel out. And let's group as, and then I probably don't want to erase that. Let's group this appropriately. Expand the, well, I'm going to group this with that. Well, let me just write it instead. So this and 2y plus k all squared. Let me distribute the negative there. Minus xy plus 2y squared over k. And I'm going to group these two together. And I'll group these two together. Factoring out, in the first case, an x. So I get y plus k minus y. And factoring out a negative in the second case, 2y plus k squared minus 2y squared. And again, if you take a step back, what is happening? You recognize this as being the derivative of y. Right? So you get x times 1. And you recognize this as being the derivative of y of 2y squared. So the derivative of 2y squared is going to be 4y. Well, I mean, nothing wrong with expanding, but what I want to convey here is the idea behind partial differentiation. And the idea is this. When you are differentiating with respect to y, you differentiate as you would, but all the variables that are not y are being treated as constant. So if you're differentiating with respect to y, x squared is constant, the derivative is 0. Derivative of x times y, this is a constant. Derivative of y is 1, so you get x times 1. Derivative of this, 4y. There it is. Exactly, right? I mean, everything comes from these limit definitions, but in the same way that we didn't spend the whole semester doing that in Cal 1, I am now moving away from the limit definition and just going to use this observation that when you differentiate with respect to one variable, all the other variables are being treated as constant. Let's take a few examples from the book. The question is asking us to find the first partial derivatives. So we're not going to resort. It is provable. You can prove it. You can prove it. We're not going to prove it. I think we have convinced ourselves, right? I mean, when you replace x with x plus h, you're really looking at the rate of change in the x direction. The y's are not moving. It's not a proof because we just did it with this polynomial function, right? But I think it's I think we've convinced ourselves enough for this class. So what are we looking for? We're looking for the partial derivative of f with respect to x, partial derivative of f with respect to y. Right? So when you differentiate with respect to x, you leave the y, you treat the y's as constant. So this is constant. Derivative of x squared is 2x. So 2xy. Derivative of 3y to the 4 is 0. Y is treated as a constant. Derivative of a constant is 0. Derivative of f with respect to y. The x is treated as a constant. Derivative of y is 1. So x squared. Derivative of this with respect to y, 12 y cubed. Thank you. This is very easy, right? You're lost on the limit to show it is convergent. I'm not sure what you mean there. Are you talking about sequences? Are you talking about the epsilon delta limit? Could we have a question saying we have to derive according to the definition? Possibly. Possibly, and that happens when you have a piecewise defined function. Even if the question isn't specifically mentioning it, then you still have to use the limit definition. We'll see an example soon. But for now, you have this function of two variables, x and t. So we can ask, what is the partial derivative of g with respect to x? Partial derivative of g with respect to x, well, the derivative of an exponential is an exponential, and then you differentiate the inside. T is being treated as a constant, derivative of x is 1. That's exactly it for the epsilon delta definition. You have to show f of x minus L in absolute value is less than epsilon. Does the first partial derivative mean the same as f1? Well, it's the first partial derivatives with an s, meaning f1 and f2. Right? Is there implicit partial differentiation? Absolutely. We'll get to that maybe today if we have time. Yeah, look, it's fine. You could write gt, partial derivative of g with respect to t. Again, it's an exponential. E to the xt times the derivative of the inside times x. Is f of yx the same as f of xy? It is not. Well, I mean, it could be. I don't know. It depends. Let's not write that. Absolutely right. As Mark suggests, we're going to move towards, they're not known as partial integrals, but rather double and triple integrals, multiple integrals, if you will. All right. Here we go. W is u over v squared. So we could ask for the derivative with respect to the first variable, u. So v is treated as constant. The derivative is, of course, just 1 over v squared. And the partial derivative of w with respect to the second variable, with respect to v, I think it's easily seen to be 2u over v cubed. Negative 2u over v cubed. Everybody with us here? Let's do a few more. I mean, are we, have we had enough? Or do we want to do a few more? Right? I mean, it does. Isn't that always the same? It starts off easy. Yeah, that's the thing. But, you know, interestingly enough, if it starts off easy and you maintain your work, it remains easy. Right? So, I mean, this is easy. After class, do lots of exercises from the book. You'll be ready for the next lecture. And the next lecture is going to be easy. And then you do stuff from the book. And yeah. What are we talking about here? 14. W1. The partial derivative of w with respect to the first variable. So 1 is with respect to the first variable, 2 is with respect to the second variable. Here we go. dg dx. What do we have here? We have something cubed. So we differentiate the cube. And then we differentiate the inside, right? Chain rule. Squared, squared, I'm just taking squared here. And then you differentiate the inside. Derivative of x squared with respect to x, that is 2x. Derivative of xy with respect to x, y is treated as a constant. Derivative of x is 1. And dg dy. Same thing, right? It's a cube. Times the derivative of the inside, derivative of x squared with respect to y, that's 0. X is a constant, derivative of y is 1. There it is. Too easy? Of course it is. with respect to the first variable doesn't mean first partial derivative. It does not. It's one of the first partial derivatives. Right? The first partial derivatives, dg dx, dg dy. Why are we referring to them as the first partial derivatives? Well, I mean, you took the derivative, you got this new function of x and y. You can differentiate that again with respect to x and or with respect to y. And there you'll get the second derivatives. Higher order partial derivatives, exactly that. It's all the same, right? I mean, think back to Cal 1, you differentiated a function and then you differentiated it again. There wasn't anything special going on there. And same thing here. What is F1? You know what it is. Very nice, Gabriel, thank you. Yx to the y minus 1. What about F2? F2? Very nice. X to the y ln x. There it is. Here we go. The f, the alpha, well, whatever. The f, the alpha. Why don't we start with df, d beta? You know what this is. You've seen this before. Fundamental theorem of calculus. Df, d beta is let me know when you're back. Thank you. Df, d alpha. Did you work that out while you were buffering? Yeah, FTC in part 1 and in part 2 as well. Right, what is the f, d alpha? You know what it is. Right? Absolutely, thank you. So, you know, I mean, we've been doing this in two variables, function f of x, y, a function of two variables. It comes as no surprise that this extends to how many variables you want. This extends to higher dimensions. Example, f of x, y, z. Y is there a minus, right? Got to flip and have it on top. Fundamental theorem of calculus tells you the derivative when x is on top. We're treating the other variables as constant. So here the beta is being treated as a constant. We have class next week. Consider this function of 3 variables now. So first partial derivatives, what is the f dx? What is the f dy? What is the f dz? Right, when you differentiate with respect to x, you treat y and z as constants. So here, the derivative with respect to x, you have an x there and an x in here. It's a product, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed. Differentiate the second one. The derivative of an exponential is an exponential times the derivative of the inside. But z is treated as a constant. Derivative of negative x is -1. There it is. David is asking what happens if the variable is on top. Well, that's what we had in the first case. df db, df d beta. Thank you, Jeremy. Derivative with respect to y. You only have a y right here. X and z are treated as constants. 2xy e to the minus x to z. Is everybody able to do these in their head? Any questions here? I mean, apart from this one, which was a bit tricky if you didn't remember the fundamental theorem of calculus immediately. Exactly. 2y, blah, blah, blah. And finally, with respect to z, this is constant. Derivative of the exponential is the exponential times the derivative of the inside. There we go. Isn't it a product rule? We're differentiating with respect to z. There is no z here. So this is a constant times the exponential. Exactly that. Consider this function of n variables. x1, x2, x3, all the way to xn. What is the derivative with respect to x1? Right? x1, x2, x3, all the way to xn. These are independent variables, very much like x, y, and z. du by dx1, what do we have? We have sine of something, so the derivative is cosine of that something. Times the derivative of the inside, which is? Which is 1. Derivative with respect to x2. Again, cosine of all that. Times the derivative of the inside with respect to x2, which is 2. And so on and so on. I think we see what's happening all the way to the end. Right? Cosine of x1 plus 2x2 times the derivative of the inside with respect to xn times that. David is asking if there's something that groups all the partial derivatives together. There is. There are actually two things that you will encounter in advanced calculus in 264. Yeah, exactly. The gradient, and something else. Yeah. Yeah, interesting. Yep. In ODs, we talked about it a bit. Yeah. All right, consider this. We have this function. We're looking for the partial derivative of f with respect to y at the point 1 and 1/2. So let's start by df dy. And you recognize that you've got a product, so product rule applies. This is arc sine of xy plus leave the y fixed. Differentiate the arc sine. I'm sure you remember the derivative of arc sine, right? 1 over the square root of 1 minus xy squared times the derivative of the inside with respect to y, so times x. So the derivative at the point 1, 1/2, what is that? This is arc sine of 1/2 plus 1 over 2 square root of 1 minus 1/4. Arc sine of 1/2, you know to be pi over 6, and whatever that is. Root 3/4, actually, the 4 and the 2 cancel. So pi over 6 minus 1 over root 3. Questions here? Well, people have been alluding to it, right? If you differentiate the function with respect to one of the variables, in this case y, you still get a function of x and y. So, in very much the same as we did in why is it not 1 over minus 1 over square root of 3, isn't it? What happened? Oh, why is it minus? Yes. Thank you. Thank you. We have reality. It is supposed to be plus. Right? So, I mean, you know, in very much the same way as with the one variable case, you have a function, you differentiate it, you still get another function. We can ask what is the derivative of that function. Same thing here. You have a function, you take its partial derivatives, you get functions of x and y. Can we not take the derivative of those functions again? You can. You can take the derivative with respect to x. Let me introduce notation to that effect. If you take the derivative of f with respect to x, if you take the derivative with respect to x again, well, you've got two d's there, so d squared, and you've got two dx's, so dx squared. Similarly, if you have df dx and you differentiate with respect to y, well, again with the two d's, so d squared f, but now you have dy dx. Similarly, the derivative with respect to y, you want to differentiate that with respect to x, so d squared f by dx dy. And if instead you want to differentiate that with respect to y, d squared f by dy squared. So you started out with two first order partial derivatives. Now you have four mixed partials, four second order derivatives. This is the notation when you're doing the D business. But you know we have other notation for the derivative, right? df dx is sometimes written this way. So if you differentiate the whole thing with respect to x, the left-hand side inherits this notation, right-hand side differentiate with respect to x twice. If you instead differentiate it with respect to y, then here you get d squared f by dy dx. Here you get f of x, y. Observe the confusion that arises. Here you do the x first, and then you do the y. Whereas here you do the x first, and then the y, right? See what happens there? See what's going on? Everybody? Right? And this notation is obviously because they're treated as operators. You're doing this operation on that thing. So it's the usual order, like multiplication of matrices on the left. But here, it's done the way you read. X first, and then y. You read from left to right. Right? This seems more logical, but this is also very logical, right? Because you're taking the derivative with respect to y of this. So that's the idea behind these things. And why don't we take a few examples? We are asked to find all second order All right. Consider this. We're looking for the second order derivatives. So let's start with the first. df dx. Derivative of ln, you know what that is. It's 1 over. Times the derivative of the inside. With respect to x, right? So the derivative of ax is a. Derivative of by, there's no x there. Derivative is 0. Similarly, df dy. Still have ln. So derivative is 1 over. Times the derivative of the inside. No y here. This is constant. Derivative is 0. Derivative of by is b. Differentiate again. If you differentiate df dx with respect to x, right, you get the second derivative d squared f by dx squared. So the derivative of this with respect to x, which you can treat as a times ax plus by with a negative 1. So you get minus ax plus by to the negative 2 times the derivative of the inside. Right, I'm treating this as ax plus by to the negative 1 for ease of differentiation. Times the derivative of the inside with respect to x. So times another a again. In other words, minus a squared ax plus by to the negative 2. If we're looking at f of xy, which is the derivative with respect to x first, and then y. So the derivative of this with respect to y, what is it? Minus ax plus by to the negative 2 times the derivative of the inside with respect to y, so minus ab. Similarly, f of yx, which is going to be the derivative of this, with respect to x, right? We're taking the derivative of f with respect to y and then differentiating it with respect to x. What do we get? Minus b. ax plus by to the negative 2 times the derivative of the inside with respect to x. And that is a, and that is 0. So minus ab, ax plus by to the negative 2. And finally, f of yy, or the derivative of this with respect to y. I think you see what's going to happen, right? Minus b squared ax plus y to the negative 2. How are we doing there? Questions? Anybody? Second derivatives or higher derivatives, right, shouldn't be a cause for concern. You're just differentiating the derivatives. Absolutely. Nothing too hard is going on. Let me bring your attention to the fact that this partial derivative, d squared f by dy dx, or f of xy, is actually the same as f of yx. Right? Or is this always true? We'll discuss that next week. Questions in the meantime? You have a question from web work? Go ahead, give it to me. Right? Tune in next week. Somebody was going to give me a question from web work. Is that coming? Very well. Ln of 1 minus 5x squared as a power series. You know what to do. What did you do? Well, what did you do? Differentiate and then integrate. Exactly. It's exactly right. Differentiate that or recognize it as some sort of geometric series and then integrate back. Is that what you did? Is that what you did? Well, did you look, differentiate and you get minus 10x over 1 minus 5x squared. Forget this minus 10x for a moment. If that minus 10x was a 1, then this you would recognize as a geometric series. Right? This is 5x squared to the n. But it's not 1, it's rather minus 10. So multiply by minus 10. I mean minus 10x. So you get your Maclaurin series, not for the original function, but for its derivative. And then you integrate. Well, first of all, yeah, okay, fine. Right? I mean, here this is going to be x to the 2n plus 1. And then when you integrate, you get x to the 2n plus 2, which could be rewritten as x to the 2n. Yeah, that's fine. X to the 2n plus 2, which you might, I mean, I don't know how web work is set up, but if you have an x to the 2n plus 2 and you want an x to the 2n instead, then you re-index. Exactly that. And don't forget your plus c, but c turns out to be 0 here. Absolutely. When do you have to re-index? When the question asks for it. Right? Here, if the web work is asking you for the coefficient of x to the 2n, and you have x, and you have stuff x to the 2n plus 2, then, I mean, you don't get this because that's not working out. I mean, I would hope, here's the thing, if this was a regular exam, you would have to prove everything. You could not assume any power series except for the geometric series. But given that it's open book and so on, I hope that instructions will be clear. Are we missing a chain rule in f of xy? I want to say that the b here is a chain rule. You're differentiating the inside with respect to y, you get b. The derivative of ax is 0. A vector parallel to the intersection of two planes. You could do cross product of the normals, absolutely. And you can also, as Dan points out, do matrix row reduction and get the actual line of intersection. All right. Thank you all for coming, guys. Well, ladies and gentlemen, you guys have a good weekend. I will see you next week. To find the series of sine squared, you could square the whole series of sine. Absolutely.